ESP, also known as extrasensory perception, is the most popular cheat feature ever created. The goal is to reveal information that you simply should not have access to. The most common form of this is known as wall hacks. The cheat will render boxes of enemy players to reveal their locations. If you've ever wondered how these exploits work, you've come to the right place, because today I'm going to explain exactly how ESPs work in the world of game hacking, so be sure to stick around. ESPs involve a lot of mathematics. I'm talking about matrices, transformations, rotations, and all sorts of trigonometry. Before you can develop an ESP, there are obviously a few requirements. First of all, you're going to need a project that lets you read and write process memory. This could be internal with a DLL, external through the Windows API, or even through the kernel with any method of your choosing. Next, you're going to need to reverse engineer the game to find the entity list, entity offsets, and most importantly for this video, the view matrix, which we will discuss later on in depth. Finally, you're going to need a way to render things, either inside or over the game, depending on your situation. If you're going internal, you can render natively within the game, whereas if you are external, you need a transparent window to render on. The job of an ESP is to loop through the entity list while filtering out undesirable entities, such as ones that are dead or dormant, because we don't want to reveal useless locations. Next, the ESP will grab the locations of the desirable players in the world. A player's location is generally stored as a three-dimensional vector, in code that looks something like this, and if you're interested in learning more about vectors, you should check out my video about aimbots in the top right. Once you're done here, of course. When we talk about player positions, we're talking about their locations within the world. We refer to this as world space. In order to create an ESP, we need to convert this 3D position in world space to a 2D position on your screen, and we do that by exploiting the computer graphics pipeline. This may sound scary, but think about it like this. All the math and geometry in a video game is done in 3 dimensions, but you're looking at the game on a 2-dimensional screen. The graphics pipeline is responsible for converting 3D scenes into 2D representations on your screen, and this is accomplished with linear transformations. At the core of every ESP, hackers use something called a world-to-screen function. Of course, you can code this function in any way you like, but mine generally take a reference to the world position and a reference to the screen position that we are calculating. The boolean that is returned will be true if the position is on your screen and false if the position is not. To make a world-to-screen function, you also need the width and the height of your display, and most importantly, you need a pointer to the game's view matrix. I've mentioned the view matrix a few times already, so let me catch you up to speed. The view matrix is a 4x4 transformation matrix that consists of the camera's location and orientation. The view matrix is used to transform world space coordinates into camera space. It does this by orienting and positioning the camera within the world. In real life, we move around the world, but in video games, we move the world around us. This is known as inverse transform. If you move an object to the left in a scene, the view matrix will move the camera to the right instead of moving the object. The most important operation you need to understand is multiplying the view matrix by a 3D vector. We do this by getting the dot product of the vector with each column of the matrix. If you've never seen this before, it might be confusing, but don't worry, it'll make more sense when we get to the code. Getting back to our function, we're going to begin by getting the view matrix and calculating whether or not the camera can even see the position in the world. This might sound strange, but if an enemy is behind you, there's no point in rendering boxes over them, because you literally cannot see them. We can determine whether something is in front of us or not by calculating the W component of the matrix. To get this component, we're going to calculate the dot product of our vector with the fourth column of the view matrix, which looks something like this. Next, we're going to check if W is near 0, because if W is near 0, it means the position in the world is actually on top or very near our camera. If the value is less than 0, the position is actually behind our camera. Therefore, if W is near 0, we're going to return false, because this thing is behind us and we don't want to render it. We're now going to calculate the transformed X and Y components in camera space. It's exactly the same as calculating the W component, except instead of using column 4, we're going to use columns 1 and 2. The first column returns the X component, and the second column gives us the Y component. We're now going to divide X and Y by W, because by doing this, we convert X and Y from homogeneous coordinates into normalized Cartesian coordinates. This is quite difficult to understand and explain, but basically, the view matrix is a 4-dimensional matrix that works with 4-dimensional data. In order to project this 4D data into a 3D world, we have to divide each component by W. If you're interested in learning more about this topic, I'm going to leave the link to a wonderful playlist of lectures on computer graphics from UC Davis Academics in the description down below. At this point, all that's left to do is to map these normalized device coordinates onto your screen. We have to do this because the normalized coordinates are in a range from -1 to 1, but we need the actual coordinates to render on our screen. We calculate the actual screen coordinates like so, where the size variable is the size of your screen. In this case, I'm using ImGUI to get my screen size. Finally, after all of it, you can return true to say that the conversion was in fact successful. You can now use your shiny new world-to-screen function to get the screen coordinates of anything in the world. Here's a short example of what ESP code might look like. We're just looping through the entity list, filtering out undesirables, and rendering circles on their heads.